Computer System Architecture Recap Lecture number 6, if I'm not mistaken. Well, we're gonna talk about recursion here, so it is the lecture about recursion and the memory segmentation. Let's go. Alright, so it is 6. Recursion and memory allocation. Exactly what I said. So let's see. We've learned something up until today. What was it? Yep, we have a stack that is extremely useful to spill registers on. And we said that anything that I might overwrite if I'm in non-leaf procedure, or even if I'm just a procedure, normal one, a leaf one. Anything that I might overwrite, I need to systematically save on the stack to be able to reload it once I'm done with my procedure to make sure that I have the original value of it. And we've seen that I need to adjust the stack first, save the things that I need to save on it, and then load them before leaving and readjust, pop out and put the stack pointer back in its original location. And the difference between a leaf and non-leaf, systematically in a non-leaf I need to save not only the things that I might overwrite or I'm overwriting, but also something systematically that I'm gonna overwrite with a non-leaf procedure, which is definitely the return address, because when I do a jump and link, whatever I'm saving in the return address register will be overridden, so I need to save it first if I'm going from one procedure to another. So what's so special about recursive procedures? Well, it's definitely a non-leaf until the very end of it. So let's see the example here. It will be easier, and we're gonna see that the same principles that we learned to now still apply. So there's my laser pointer. Right, so I'm having some kind of factorial here. I have an initial value that I'm putting in one of the registers, and as per convention, the register that I'm gonna use is one of the A registers. So basically, if I'm saying that A0 has the value of represents the value of a variable n here, so systematically, if I'm gonna call back myself, so I'm getting into the recursion, so I'm systematically overridden whatever I'm using here at A0. Unlike normal non-leaf procedures or procedures, in a sense, I could have used A0, A1, etc., anything, so I can avoid the need of splitting onto the what do we call it, the stack, right? However, in order to illustrate, we used on purpose in the previous examples the same registers in order to show you that I need to split them on the procedure on the stack. Here I don't have an option, because in recursion, well, it's always be the same one, so basically I'm gonna stick to the same register, so I need to save it first in a way or another, because I'm gonna override it somewhere. Right, so what's going on in here? If n is less than 1, that's it. That's the leaf segment of my recursion. If it's not the case, well, I need to go ahead and subtract 1 from n, call myself with that new value, and then multiply the result and return it. By the way, where do I return? What kind of registers, as per convention, I should use for the return values? We already know that it's the V registers. So yeah, basically what I need to do is, because I'm doing that, because I'm having the non-leaf version, the non-leaf section of it, and the leaf final one, well, at least I need to go ahead and deal with the stack. Fair enough. Non-leaf means that I need to systematically save the return address for sure, and because I'm using the same register, I don't have a choice here for the parameters or the arguments here. So I'm going to save A0. Then I'm going to go ahead and test whether I'm going to go to the leaf section or to go ahead and call back myself. So if it's the case, if n is less than 1, all I need to do is stick 1 into V, right? Clean up after myself, because I've done here. So I need to clean up after myself and return to my caller. This means that the very last non-leaf version of me. Alright, here's the case. Well, if I'm not here, I'll be here. So what should I do? I need to subtract 1 from the original value, call myself with that new value, right? Because each and every time I'm getting into that, I need to clean after myself, right? And the idea here, using whatever I got from me calling myself with a new value to the original value that I've saved, get it? And I pop now, in addition of course to the return address, right? And then I'm gonna stick it to v0 here, and that's it. I'm gonna return the call. So basically this is exactly what I need to follow up. So you can feel that we're covering both the leaf and the non-leaf, both in recursion, and the only difference, I would say, that the use of the register here is mandatory. So it's always the same register. I cannot have, you know, on one time use A0, A1, etc., etc. It's if I'm using A0, I'm sticking to A0 everywhere. Fair enough? What now? Let's see it exactly step by step. So in MIPS, that would be the label of my function, adjusting my stack because I want to save some stuff on it. So using the stack pointer and the offset here. How many things do I need to save? We've seen that we need to save the return address for sure, because there's a non-leaf, there's a non-leaf side of it, and then I need to definitely save the one that represents the arguments here, because it's going to be overridden for sure. Alright, so here is where the testing this is where the testing happens, right? Set on less than. What does that even mean? Let's find out. So I'm comparing my n, right? So the A0, the original n that I have here, to 1. If it's less than 1. So if it's less than 1, this means that I'm gonna set T0 here. And if it's not less than 1, this means that T0 is not equal to 0. So if it's less than 1, this one will be 1. If it's bigger or equal to 1, this one will be 0. So if it's the case, well, I'm gonna go ahead to the label here. So n is, this means that n is bigger or equal to 1. Fair enough? Right, so let's see. If the branching is not happening, so if it's the case here, if I'm not branching, so I've tested that, this is not happening, I'm not jumping to the label to L1 here, I'm going to continue. So what would happen? This means that I'm in this case here, so I should return 1. What's the easiest way to do that? Well, I'm going to add 1 to register 0, which always has the value 0, hardwired, right? So 1 to 0 and put it in V. Fair enough? And all I have to do now is to readjust my stack and jump to the return address. I haven't loaded it. That's weird. Well, that's not weird at all, because again, see here, I didn't mess with it. I didn't override it still. So I didn't need to load it. So this is what I'm covering here. It's as if I were the leaf procedure. See? We're gonna find out where I'm gonna load them back. It's definitely in the non-leaf segment of it. Right, so L1, let's do that. What should I do? Take 1 out of n, put in A0, and go ahead. go back to facts. I'm calling myself now with that new value. Tuck, tuck, tuck. And I'm gonna jump back to, once I'm done, I'm gonna return to this very here. So this is where I need to make sure that I'm back to the original n. It's not the n minus 1 anymore. So to the original A0 that I've saved before, and to the original return address that I need to go back to, right? And readjust again my stack pointer here. Whatever am I here, I need to clean after myself. So whatever I did here, I need to do it here or here. Last thing to do, now that I've popped the original value of A0, right, all I have to do is multiply it with the V that I got from the previous, all the way to the first one. Fair enough. Multiply and put it in V0. Now I can go back to the original return address that I saved on the stack earlier. Fair enough. Go ahead and trace it with n equal to, and you can understand the logic behind it if you did not fully understand it with my high-level explanation. It's always practical to trace with a pen and paper. All right. We've learned those. So basically, we've seen that as per convention, we have a bunch of stuff that are reserved for the assembler and the operating system and this compiler, etc. As per convention, nothing, prohibits you from using them virtually for anything. But I mean, in order to make sure that everyone is understanding and everyone is on the same page, it's better to use the convention. Arguments and of course you know that by now, so the A0s, the V's, etc. The A's and the V's. And things that we need to save to be used as per convention for the the S registers as per convention for the saving. One last thing that I wanted to talk about, I just wanted to introduce, to be honest. So we've learned that the stack grows down. Each and every time I'm going to save some stuff, spill some stuff on the stack, I'm going to spill them, and then in the LIFO way, I'm going to take them out. And here in class, I've showed that to some people and I asked a question, and we've noticed that sometimes some people, you can notice that here I'm having argument 6 and argument 5. What would those be for, and why the heck am I saving them on the memory here? First off, we've noticed that the MIPS people decided that only 4 registers are more than sufficient for 99.9% or whatever, 90% of the cases out there. So if I'm using A0 to A3, those be sufficient for most of the functions out there, to translate most of the high-level functions out there. However, sometimes you're gonna notice that some people use more arguments. So basically, if it's the case, well, I can either use any of the available 32 available registers for some reason, or if I wanted to be on the safe side, and then this is what, again, it's the good practice, I can go ahead and systematically use the memory. So there's a trade-off here. Where is the trade-off? Knowing me by now, it will affect performance for sure. How come? Well, if you're saving things on the memory, of course you have more flexibility because the memory is relatively big compared to the only 32 registers that you dispose of in a way or another, and especially the 4A registers that are dedicated for convention-wise, dedicated for the arguments. Well, here you can virtually have a zillion arguments saved on the memory. So this is flexibility, awesome. What is the counterpart of it? What downside of it? Well, you're gonna go ahead and get it from memory, and getting it from memory, well, it takes more time than getting it from registers. So you're gonna be penalized timing-wise. So it's always a trade-off. Alright, so my stack grows down, especially we've seen that in the particular case of the recursion. Well, we're gonna go ahead and keep on adjusting the SP, and it will grow down so I can tell where it's pointing at, the last word that is pointing at, and this is what we learned till now. However, how would I know where it started? Where does my frame start? So someone suggested, even before showing that slide, that maybe it makes sense to have another pointer saying that this is the beginning of my frame, and it is exactly the case of the MIPS people and many others actually, to use a frame pointer to keep track of the beginning of the base in a way or another of your frame. All right. Last thing that I'm showing is the memory allocation convention. So we have four bytes, 4-byte words here, and we can go from address 0 all the way up to address something here. What would be the all the way up to address here? Of course, again, in MIPS we're using byte addressing, so it's the beginning of the, I mean, if we would say it should go to FFFFF all the way FFFF, because we're gonna go 4 bytes means that we're using 32 bits, and it's from 0 to 2 to the power of 32 minus 1. Fair enough. So this is the roof of my memory, the top of the memory. Fair enough. And at the very beginning of this course, I believe that I talked to you about two different physical implementations of memory. Whether we're gonna save, I mean, the memory is there to save two things, data for sure, and another thing, and the other thing is instructions. So basically, if you have a same memory for same physical memory for both instructions and data, this is one type of architecture, and if you have separate memories, this is another type of architecture. And you should know it by now, so I'm not going to repeat it today. The idea here is, well, I know that this is from a processor point of view, this is what the CPU is seeing whenever it wants to talk to the memory. So basically, well, it's easier to say now, well, if it's using, I don't know, von Neumann, for instance, well, which section is dedicated for the instructions, and which section is for the data, and which section is for the stack, and which section is for something else. So it makes more sense to segment the memory into different parts. Fair enough. And this is what we're gonna see from now on. I don't care about that. Already explained that. And yep. So here, first two things. At the very beginning, there's a segment, and at the very end of the memory, there's another segment that is reserved for something, and it's reserved from the other course that you're having with me. It's reserved for the kernel. So one of them is for sure you're gonna store something related to, I don't know, so a program is made out of processes, or a program is made out of threads, or at least a program is a process, right? So fair enough, in order to be able to manage the different processes, well, there should be somewhere when I'm gonna store some information regarding that process. And by the way, what is that information called? It's called the PCB, the process control block, and this is where it should be saved. So here you have something, and here you have something. Well, actually this one is empty, but it doesn't really matter. Alright, so these are reserved for the kernel, and then I have the stack that goes down. So you can notice that I have the top of the stack, and then it has no end until the very here. So I have a lot of room here for some reason, and we're gonna see that. Why do we have that? Because first off, we can never guess how big the stack is. So basically, it can grow all the way to somewhere. There's always a limit, because if you get to that limit, well, you will notice that your computer, your kernel, will be unhappy about it, and it will utter that you're having a stack overflow for some reason. Right, so this is the stars, goes down, and then I have a section for the instructions for sure, which is relatively smaller than the one for the data. Makes sense. Later, And everything that is being global or static, well, should have a place for it. Fair enough. Um, and this is, you're gonna have it on the tutorial, and for that static data you'll have some kind of global pointer, and you're gonna tackle it in the tutorials. Doesn't really matter. So see, instructions, kernel, stack, instructions, some static data, you know, global variables or static. Almost done, almost. There's still one thing here. So this one is growing down. There's something else that grows up. What would that be? So we've covered the static data, and you as software engineers, well, if things are not static, they could be dynamic, right? And I believe that you've seen static data structures. For instance, an array, could you change its dimension at runtime? Can you define a dynamic array, like with the array normal keyword? Normal array keyword? Well, naturally no. You need to fix the size of the array inside of your code. You cannot just ask the user to enter the size of the array. It wouldn't work, because an array can be seen as static. However, in Java and things like that, you've seen that there are other structures that could actually change during runtime, during execution, such as vectors, lists, etc., etc. And these are what we call dynamic data. And dynamic data is also known as the heap. This is where we're gonna save them on the heap. So the stack grows down, the heap grows up during execution. So if you need to have a bigger, I don't know, a vector, linked list, whatever, it doesn't really matter. Well, each and every time you're gonna add a cell to it or something like that, well, it will grow in the heap. And you can notice that they design it in a way that we have some room here, some common ground. Well, if the stack is big and the heap is small, well, we're good. So we can use in a smart way the space that we have here, and the other way around as well. Alright, so that's pretty much it for that lecture. This is what I need you to know, and that's it, I think, for the coding part and the ISA part. And starting next time, I believe that we're gonna tackle the hardware implementation, which is a lot of fun. Alright, so you can do some research on your own and have fun learning. See you soon.